When man first began building tools, his concern was how they would help him get food or protect him from his enemies. What he didn't expect was how they would give him more time to look around him, to wonder about the sun moving across the sky, to ask where the wind came from, or why did mountains sometimes throw fire at him. He began to build mental pictures to explain these phenomena, and since he had no idea how to find the reasons, he made them up, along with various myths and an endless supply of gods. As man became more sophisticated, he was less satisfied with the old solutions. He wanted more concrete answers, but he had to learn how to measure these phenomena. And of course, there had to be some way to deal with his resulting measurements. The activity of a modern-day physicist proceeds in two distinct but overlapping areas: modeling and measurement. Mathematical modeling is a term used to describe the process of building a mental picture, complete with symbols and a set of rules for manipulating these symbols. A physical measurement is the procedure whereby certain parameters of a collection of matter and energy are observed and recorded. Earlier on, it was found that the whole process of measurement could be made more easily by the use of standards of measurement. Originally, standards of measurement were based on such things as hands, feet, stones, and horses. As scientific measurement became more precise, better and more easily reproduced standards were required. These standards simplified and sped up the evolution of mathematical models. The use of mathematical modeling and physical measurement can be demonstrated with the aid of a weight suspended on the end of a length of string. The ball is pulled to one side and released, resulting in regular oscillations. If the string is lengthened and the ball again set in motion, we note the same kind of oscillation, only the time it takes to swing back and forth is longer. From this observation, there appears to be some relationship between the period of oscillation and the length of the supporting string. This can be checked by measurement. We could measure the string with our fingers, which are rather handy, or we could use barley corns, a bit more accurate, but very tedious. Likewise, several kinds of timing devices are available, such as heartbeats and egg timers. When hands and heartbeats are used to make the measurements, the following table of results is obtained. For a more meaningful look at these numbers, the time of swing can be plotted on a graph against the square root of the string length. There is a suggestion of a straight line, but the deviations from this line are quite large. Perhaps our measurements are at fault. When we use more accurate measuring tools, such as a stopwatch and a meter rule, a new set of numbers is recorded. When plotted on a graph, these new measurements also indicate a straight line. Only this time, the deviations are much smaller. Here, the builder of mathematical models, or the physical theorist, enters the picture. He introduces the notions of mass, acceleration, velocity, and gravity, and produces the following mathematical expression, where t is the period in seconds, L the length in meters, and g the acceleration due to gravity. In this theoretical expression, if t is plotted against the square root of L, a straight line will result. However, experimental points rarely lie on the straight line produced by the mathematical model. If the average deviation of the experimental points from the straight line is less than the error which is due to bad rulers and clocks, then the straight line, or mathematical model as it is called, is said to describe the experiment. Model building, however, is not a finite process. Every model is based on previous ones, and in turn provides material for further development. A model which has been in the process of development for the past 2,000 years is the model of the atom. As early as the year 400 BC, Democritus was theorizing on the composition of matter. The only existing things are atoms and empty space. All else is mere opinion. The properties of his atoms were those of position, shape, size, and motion. He presumed these atoms to be indestructible, infinitely numerous, and in ceaseless motion. Centuries later, his views were being restated by philosophers like Bacon, Descartes, and Newton. The discovery of chemical elements, the law of conservation of mass in chemical reactions, and the law of definite proportions enabled the English chemist and physicist John Dalton to create and justify his atomic picture of matter. Dalton's atoms for a given element are identical in weight and every other property. They are indestructible, with chemical reactions implying merely rearrangement of the atoms. Based on experiments by Gay-Lussac in the early 19th century, the Italian Avogadro proposed that equal volumes of different gases at the same temperature and pressure contain equal numbers of particles. It thus appeared that gaseous elements existed, not as single atoms, but as pairs of atoms. In the succeeding decades, scientists found that the atoms of each element all had the same weight, and tables of their atomic weights were accumulated. Since oxygen combines with most elements, its atomic weight became the standard and was defined as precisely 16. This scheme of atomic weights was to be revised in 1961, when it was discovered that 3 isotopic forms of oxygen exist, all with different atomic weights. While doing research on mass and charge, J.J. Thomson began to theorize on the structure of the individual atom. He presumed that atoms were made up of a positively charged substance in which was embedded the much smaller negatively charged electrons. He determined that the mass of the electron in the hydrogen atom was only 1/1837th of the total mass. At the beginning of the 20th century, Nagaoka proposed a Saturnian atom. The electrons revolved around a central nucleus like the particles of Saturn's rings. The evidence for this model came from a series of experiments on the scattering of alpha particles by matter. In 1911, Rutherford worked out the theory of scattering for alpha particles, assuming that the alpha particles are repelled by a concentration of positive charge. A picture began to emerge of an atom with a structure in which nearly all the mass is concentrated in a tiny volume of 10 to the -11th, the total volume of the atom. Outside this nucleus were a number of electrons at various distances, up to a distance of 10 to the -8 centimeters. In 1913, Niels Bohr proposed his immensely successful theory of the atom. He stated that electrons were locked in specific orbits. They could not emit any energy while circling in these orbits, but should one move from its orbit to another one, closer to the nucleus, it would give off energy. In order to move to a more distant orbit, the electron must first absorb energy. As you can see, the atomic model is constantly being revised, and probably will be for a long time to come. In fact, there really is no end point to this process. More solutions invariably lead to more questions. This refinement of models is more than an idealistic search for pure knowledge. Physicists must also bear in mind the application of their mental pictures. Before a bridge or a new aircraft can be constructed, countless mathematical models must be applied to determine what materials to use and how to design and assemble them. When the big jumbo jets were only drawings and calculations on paper, the builders knew the flight characteristics, payload capacities, and most important to them, how much they were going to cost. Without the planning ability made possible by the physicist models, these massive projects could not even be considered. Let us summarize the various points we have made. First, the conceptual picture of the universe evolves with time. New experiments suggest new pictures. New pictures suggest new experiments. Secondly, physics involves experimentation and model building. Experimentation involves the intelligent manipulation of matter and energy. Model building involves the intelligent manipulation of pad and pencil. The two activities must complement each other. Otherwise, each is an exercise in futility. Third, models of the universe are developed over long periods of time by many people performing many different types of experiments and calculations. The new models of the atom and the universe are not the last word in description. As new experiments are performed and new data collected, new mental pictures will have to be created.